All right. Okay.
I got a 20.
All right. So yesterday we were talking about electrostatics. We started talking about electrostatics. Don't pay attention to this or this. I'm just leaving that up for chemistry because chemistry is doing a little project. So we were talking about electrostatics, and once again, electrostatics means static charges not moving. Or when point charges create fields, we're talking about the fields that the point charges create. That's electrostatics. When you have two charges in space, then you get a electrostatic force according to Coulomb's law, which is going to be Coulomb's constant, 9 times 10 to the 9, times the charge of body 1, charge of body 2, divided by the mass, or divided by their centers. It's just like universal gravity with mass. Works exactly the same way. Biggest difference is that universal gravity is always attractive. Is electrostatic always attractive? No. When is it attractive?
When they're opposite charges.
When there's opposite charges. And when is it repulsive?
When they're similar charges.
When there's similar charges. Good. So there you go. Any questions about this? All right. Cool. Okay, then we have the fields they create. A positive field is an outward pointing field. A negative field is an inward pointing field. And much like weight, when you have mass and a gravitational field, you have force, electrostatic force, when you have a charge in an electric field. Okay. Put a charge in an electric field, that field, or that charge is going to feel a force either towards the center of that field or away from that center of the field. And then how do you know how strong the field strength is? The field strength is given to you by Coulomb's constant multiplied by charge divided by the square of the distance from the center of that field. Cool? Okay. I think this is where we ended. Yeah, this is where we ended. Okay, so just like an object in gravity has a potential to fall, if you put a point charge in an electric field, there is a potential for it to move towards or away from the center of the field. And by convention, what we say is the potential is how much energy it would take to place that particle in the field. It's very strange. It's how much energy would take to take that particle from infinity or anywhere and drop it in the field. Potential is given the variable V. This is one of the few times where the variable and the unit are exactly the same. V for volts. Volts is V, potential is V, and the unit, the variable and the unit are both V. Yay. Okay. One of the few times that actually is the case. Actually, I will erase these. These are getting up in my PowerPoint. Okay. So V is the electric field potential in volts. D is the distance from the middle of the field. And then E is electric field strength. And we came up with a unit for electric field strength yesterday. So what was the formula that used electric field strength yesterday?
E equals K Q1 or D.
Okay. Was there one that was just 3 variables like that? It had an E in it.
F equals QE.
F equals QE. And F is a Newton and Q is a Coulomb. So we learned that the unit for field strength is the Newton per Coulomb. Right? Because the variables need to change or they need to cancel out on both sides. So here you have a Newton, Coulomb divided by Coulomb gives you a Newton, and now you have a Newton equal to a Newton. Make sense? Now look at this variable, or this equation. This is delta V equals ED. The variable for potential is volts. The variable for distance is meters, which means the variable for electric field strength has to be what? Volt over meter. So what this means is electric field strength can be Newton per Coulomb or volt per meter. And what's really cool is it can be both. So you can basically say, I'm going to put an equal sign in there. So a Newton per Coulomb is a volt per meter. A Newton per Coulomb is a volt per meter. Wait. It's kind of one of those little handy relationships that you need a ball. Oh, you're just like, everybody needs a ball. So does this idea make sense?
Oh, yeah.
Okay. You can be honest with me. If it doesn't make sense, you can just say it doesn't make sense.
I get some of
Okay, we're getting there. Again, you probably never actually learned anything about electrostatics before yesterday. So it's probably new and different, and we're getting there. Okay, so imagine you got a field, got an electric field. The potential is how much, I wish I had a good analogy for this. The potential for it to move in the field is given by the distance from the particle. These actually should be from the centers, not the distance. They should actually be from the centers. Center of the particle, the center of the field, and the distance away. It is the potential for it to move. In a 9-volt battery, there's an anode and a cathode. Those are words we're going to use a lot next unit. So there's an anode and a cathode. You got a 9-volt battery. You know what a 9-volt battery looks like. This is a top view. The little one is positive, and the big one, and a 9-volt battery.
What? One of the little things like.
Oh yeah. Okay, I see what you're saying. Yes. Right. The anode is a hexagon. I see what you're saying there. Yes. I'm going to make it an octagon because I want to. So anyway, so the anode is the big one, and it's negatively charged. And what it basically means is this: if you were to somehow, you could see electric fields, the positive charge would be creating an outward electric field, and the negative charge would be creating an inward electric field. And at any point in between those two, you could determine what the field was because you know that overall voltage is 9 volts. The overall potential in the battery is 9 volts. So you could say, what is the electric field from any point in here? You basically say, all right, if I know the potential is 9 volts, I'm going to say the positive is +9 and the negative is 0. I could say the positive is 0 and the negative is -9. But when you have a 9-volt battery, that means the difference in potential from the high to the low is 9 units of potential. Think of it as the height of a waterfall. Water has the potential to fall over the waterfall, and its potential to fall is a distance. Kind of, yeah. It's like a magnitude of fallingness, of potential fallingness. Well, electric fields do that too. So if you have a 9-volt battery, that means you basically say, I'm going to make the positive 9 and the negative 0. You also have your favorite 1.5-volt battery, a little nubbin on the end. So it's 1.5. This is your A, or your AA or your AAA. And the positive end, there's a positive and a negative end, it's 1.5 volts. So you see the positive end is 1.5 volts, and the negative end is 0 volts. So far so good? So I want to know what the electric field is 1 centimeter from the end of my 1.5 volt battery. You just say, all right, there's 1 centimeter, and the electric field is going to be my 1.5 volts divided by my 0.01 meters. Make sense? So at one centimeter away from the end of my 1.5 volt battery, I have, what is this, 150 volt per meter? I don't think so. No squares. Okay. Does that idea make sense? And if I asked you, what's the electric field 10 centimeters away from my 9-volt battery, like, what is it right there? You'd say, all right, my electric field is my 9.0 volt battery divided by 0.1 meters, so 90 volt per meter.
What formula are you using?
So would that,
Are you using that one you just?
Yes, V equals EV,
Okay.
yes. Yeah.
so would that also be 90 coulomb or 90
No, we'll get there. Oh, yes, yes. 90 newtons per coulomb. Yes. Yeah. Newtons per coulomb, yes. I thought you were going somewhere else, but yes, 90 newtons per coulomb. So you could basically say 90 volt per meter is also 90 newtons per coulomb, which means if you drop the coulomb of charge right there, it's going to feel 90 newtons. It's going to experience 90 newtons of force depending on either towards or away from the center of that field. That's a very good point. Everybody understand what I just did? Some of you are like, no, I don't want to admit it, Doug. I don't think my friends think I'm stupid. So if you got a field strength of 90 volt per meter, and then you drop the charge into it, it's going to feel a force. And how much force it feels is going to be given by the field strength equation over there, which is F equals QE. So if you have a field strength that's 90 volt per meter, it's also 90 newton per coulomb. So if you drop the coulomb right there, it's going to feel 90 newtons of force either towards the center of the field or away from it. All right. So, give me a thumbs up if this is kind of making sense. Guys, making sense to you. All right. Anything else? Oh, equipotential lines. So equipotential lines are kind of cool. Basically what they mean are they're lines where the potential is the same. Okay. That's what it means, equipotential. Have you ever seen a topographic map where it shows elevations on a map?
Yeah,
So a topographic map is kind of interesting. So basically, let's say you have a mountain here, and then you have a mountain here. It'll show like this is 1,200 feet, and this is 800 feet, and this is 600 feet, and this is 1,000 feet, and this is 1,200 feet. Yeah, topographic map. Well, that's basically how equipotential lines work too. So you basically say at every point around this, it's all the same voltage. So this is all 150, well, 1.5 volts, whatever that is. So this is going to be, they're going to go out and they're going to radiate out equal potential lines. We're going to investigate this tomorrow in lab. So just realize equipotential means equal potential lines. Okay. How are we doing? Give me a thumbs up, you're ready to move on. Cool. All right. Now, to move a object through a gravitational field requires what? Energy. Exactly. It requires force over a distance, but it requires energy. So to move my ball from here to here, I am increasing its potential energy, which means I have to give it energy to increase the potential energy. Make sense? Okay. Similarly, if I harvest the potential energy, I can get kinetic energy out of it. Okay. If I go from potential energy to this, potential energy to this, I harvest the potential energy, and that gives me kinetic energy in 1/mv squared, mgh. Okay. Same thing. So if you put a particle, a charged particle, in a potential, it's going to take energy to push that charged particle through the potential. Okay. So there's a potential. I'm drawing the potential as like in a downward direction for reasons that hopefully will make sense in a little bit. Then I'm going to put a particle, I'm going to push that particle through the potential. The amount of energy it requires to push a charged particle through a field is given by the charge of the charged particle multiplied by the change in potential. That's how much energy it's going to take to push it through the field. So, this is very similar to a change in potential energy, delta PE grav, is equal to M, and then GH is the volt, is the potential equivalent. So, in order to push a mass through a gravitational field, you say, all right, this is going to be the mass I'm pushing, multiplied by the field, multiplied by how far I push the mass through the field. Does that make sense? So you've done this before. If I take my ball, I find the mass of my ball, multiply it by 10, and then how far I push it through the gravitational field is how much potential energy it gains. Make sense? Okay, so same thing with the charged particle. You take the charge of the charged particle and you just push it through a potential. So let's say this is a 2 coulomb charged particle, and I'm going to push it from 8 volts to 4 volts. That's a bag time. 8 volts through to 1 volt. So we have a delta V of 7 volts, so it's going to require 14 joules. So I'm pushing a 2 coulomb charge through a potential of 7 volts, it's going to require 14 joules. Does that idea make sense?
Yes.
If I pushed a half a coulomb charge through that same potential, how much energy is it going to take? 3.5 joules. Cool? All right. Remember what I talked about yesterday, that there's this word called quantized? So quantized are basically the small, or packets of things of a very specific size. If you go to the grocery store and you want to buy Twinkies, you can only buy them 1 Twinkie at a time. You can't buy half a Twinkie. It's a quantized value. You can buy a single Twinkie, or a packet of 3 Twinkies, or 4 Twinkies, or a dozen Twinkies, but you can't buy a half a Twinkie. Make sense? Similarly, there is a quantized value of charge. The smallest amount of charge that can exist. Does anyone know what it is? What is the smallest charge that can exist? You can't have a fraction of that amount of charge. Ooh, I wonder if Alexa knows. Alexa, what is the fundamental charge of an electron?
The electron's charge is minus 1.602 times 10 to the negative 19th power coulombs. Did that answer your question?
Yes, it did. It is
Great.
negative 1.6 times 10 to the negative 19 coulombs. This is, get ready, Q sub E. It is the fundamental charge of an electron. It is the smallest charge that can exist, and every charge will be a multiple of this value. I think it's on your formula. E, yep. Oh, they made it positive. Come on, College Board. Okay, so this is the AP Physics 2 formula chart from last year? Either last year or last year. It has a couple of annoyances. I'm not going to call them errors, but I'm going to call them annoyances. And this is your new formula chart. Yay, you get to use this on everything you want.
Wait, so we don't need the other one?
Let me need the other one. So the AP Physics 2 test has all the AP Physics 1 formulas already built in. So this is your new formula chart. You might notice I already made a change for optics, because optics, they put absolute values around magnification, and they really should not have done that. It really should be M equals HI over HO equals negative DI over DO. They put absolute values over there. The reason they did that is very few physics teachers teach optics, so they tend to accept positive and negative values. They're like, well, the answer is actually negative 3.5 magnification, but I'll accept 3.5. I think that's stupid, because the magnification gives you a lot of information about your image. So I don't like that they did that. So there you go. You also might notice they use S sometimes instead of D. They use SI and SO for height of, or distance of the image. This is the object, but anyway, that's neither here nor there. Okay, so this is your formula chart. And you'll notice right there at the very top, it says electron charge magnitude E equals, should be negative 1.6 times 10 to the negative 19 coulombs, because electrons are negative. But remember how I said about conventional current is made positive just because? Yeah, that's what they're doing. All right. Question?
So would the 1 electron volt be positive, or would that also be negative?
Excellent question. And that's the next thing we're talking about. The electron volt is a special unit of energy used in quantum. We will use this in May. I think we're going to get to quantum in May. We're going to use this in quantum. The electron volt is a special unit of energy used when you're talking about a couple electrons at a time. And when we're talking about quantum, we are talking about a couple of electrons at a time. When we're talking about electrostatics and how much charge builds up in your hair when you're rubber with a balloon, we're talking about trillions upon trillions upon trillions of electrons. So we use coulombs. Make sense? When we're talking about, like, instead of molecules in chemistry, we use moles for a lot of molecules. Well, in physics, we use coulombs for a lot of charges, but when we get to quantum, we care about just a few electrons at a time. And the energy of an electron volt is the energy that it requires or requires when we push a single electron through 1 volt. If you push a single electron through 1 volt, it requires an electron volt. That's what they called it. The atom smashers that we have that launch, that speed charged particles up really fast and smash into things, are rated in thousands of electron volts, keV, millions of electron volts, MeV, or billions of electron volts, GeV, or quadrillions of electron volts, TeV. Clark. Clark, look at Clark. Congratulations, Clark.
Yeah, Clark.
These are sports photos. It's an action photo of you like faking the phone coming at you. Okay, so you come back to me. Thank you. So when you take the electron and you push it through a volt of potential, it's going to require 1 electron volt. If you push it through 6 volts, it's going to require 6 electron volts. If you push 2 electrons through 6 volts, it's going to require 12 electron volts. See how it goes? Now here's the thing. A coulomb is a whole bunch of charges. Times 10 to the negative 20, or 10 to the 25th, I think, or 10 to the 18th. I told you at the beginning of the thing. So a coulomb is a whole bunch of electrons traveling through or as a charged particle. If you push a coulomb through 1 volt, you get 1 joule, or it takes 1 joule. So a coulomb through 1 volt, 1 joule. 3 coulombs through 1 volt, 3 joules. 3 coulombs through 2 volts, 6 joules. So a coulomb is a whole bunch of charges. An electron is just a single charge. Electron volt, single charge through a volt. How are we doing? Okay. Now, where did this number come from? We just pulled it out of our butt, right? How do we come up with this value? It's such a teeny, teeny, tiny value. It's extremely small. I invite you to do anything that produces a single electron of charge. A single 1.6 times 10 to the negative 19 coulombs of charge. How do we come up with it? science, one of the most brilliant experiments in just ever. This guy named Bob Milligan, he devised this system. So, round about 110 years ago, he devised a system. And what he did is he took a device, he took basically a can that had some chambers.